Okay, so here's your next question. I know we're starting with question 5 here. 1 through 4 are on a previous video. So the way this is going to work, I'm going to put the question up here, okay, and then I'll give you some time to work it, and I will pause the video obviously while we do that, and then we'll come back and we'll talk about the answer, and then we'll go on to the next question. Okay. All right. So this question, it's talking about 1-propanol, and it's telling you the normal freezing point. So it's asking, is this an endothermic or exothermic? And then it just gives a bunch of questions here about spontaneity and equilibrium. Okay? Spontaneity is a word. All right, so I'm going to go ahead and pause this. I'll give you some time to work on it, and we'll come. All right. So I'm going to, again, this is just for the benefit of the video, I'm going to actually be writing out the answers to all of these things on the next slide, so that if you want to, you can just go to that slide and, you know, on the video, and then look at the answers. So you don't necessarily have to listen to the explanations if you just want to see the answer. So letter A is the freezing of 1-propanol, an endothermic or exothermic process. Okay. I'm hearing a lot of exothermic, okay? And exothermic is correct on this one because what it has to do, in order for it to freeze, it has to release some energy, right? Okay, so it's giving off energy to the surroundings, so it's going to be an exothermic process, which, again, it's a little bit weird to think about it that way, but freezing is exothermic. Okay, in what temperature range is the freezing of 1-propanol a spontaneous process? Okay, the freezing would be spontaneous below 127, right? Okay. Okay, so below 127 degrees Celsius, because that is the freezing point, anything below that is going to be spontaneous. It will freeze below that temperature, okay? Non-spontaneous, obviously, then is going to be... There you go, good, above 127 degrees Celsius. And if this wasn't obvious enough, what is the temperature at which liquid and solid 1-propanol are in equilibrium? 127 degrees Celsius. Okay, so at 127 degrees Celsius, because that is the freezing point / melting point of that particular thing, remember, at that point, you've got solid and liquid in equilibrium with one another, okay? How do I want to say that? At the freezing point, solid and liquid exist in equilibrium. That's kind of the definition of the freezing point. If you want to get even a little bit more complicated with your explanation there, you could say that the at that one particular point, that's a horrible and. That's not better. That's not better at all. There you go. Okay, so solid and liquid exist in equilibrium. We'll just stick with that for now, because we got to make sure we get through this. All right. So there's your answer on that one. Number 6. Give an example of a process in which the entropy of the system decreases. And what is the sign of delta S for that process? Okay, so I'll give you a second to come up with that. This one's a little more open-ended. Alright, so for this question, an example of a process where the entropy of the system decreases. Give me an example that's not one that we, talked about. Synthesis of iron 3 oxide. Okay, so I'll go with that, okay? So the example there, iron 3 oxide is going to come from iron, which is a solid, and oxygen, which is a gas, right? Okay? So if you've got a solid and a gas, and you're turning that into a solid, iron 3 oxide is going to be Fe2O3, okay? And we've taken something that was a gas and we've turned it into a solid. Okay, So that would be an example. That's a good example of a process where entropy decreases. Okay. All right. The sign of delta S for that process is going to be negative. All right. All right. Oh, wait. I'm not going to stop that yet. All right. Question 7. Normal boiling point of methanol. And it's giving the molar enthalpy of vaporization, okay? And it's asking a couple questions about entropy and about the delta S here. Okay, this one's a little bit tricky, so you might have to think back to the beginning of the unit on this one. See if you can figure this out. All right, so let's go ahead and talk about this. The first part I think we can probably figure out. When a liquid boils at its normal boiling point, does its entropy increase or decrease? Yeah, increase. If something goes from a liquid to a gas, the entropy is going to increase. All right, so the answer to part A here is increase. All right, now the second part is the tough part here, okay? We want to calculate the value of delta S when 1 mole of CH3OH is vaporized at 64.7 degrees Celsius. You're going to have to think back to the beginning of the unit for this one, because what I kind of wanted you to remember, or just refresh yourself on, is where delta S comes from in the first place, okay? And it's actually related to the Q, reversible, okay, divided by the temperature. You guys remember that? Delta S equals Q rev over T. Now that equation is not on your AP equation sheet, so I don't know that they would actually ever ask you to do a calculation like this. But I think it's just good to know where the delta S comes from, how it gets calculated, okay? So if we can have something at its boiling point, its normal boiling point or normal melting point or something like that, and we know the delta H associated with that, and we carry this process out at a constant pressure. I don't know if I said this in any of the videos, but at constant pressure, Q is equal to delta H. Do you guys remember that from Unit 5? It was a long time ago, okay? So, if our formula here is delta S equals the Q reversible over T, in this case, assuming that we're doing it in an open system at constant pressure, it's also equal to the delta H over T, okay? And the temperature does have to be in Kelvin, not in Celsius, okay? So the delta H here for vaporization is 71.8 kilojoules per mole, okay? So this is going to be 71.8 kilojoules. Now, it's kilojoules per mole, but how many moles of this substance are we vaporizing? 1 mole, so the number's the same. Divided by the temperature, which is in Kelvin, which is going to be 337.7 approximately. Okay? So then your delta S here is going to be 213, sorry, kilojoules per Kelvin. And if you leave it like that, if the problem doesn't specify what units it needs to be in, that's okay. All right. Typically, delta S is reported in joules per Kelvin instead of kilojoules. So we might want to change this and say 213 joules per Kelvin. Now, it's always a good idea to check your sign at the end of this. And you could put per mole times Kelvin, right? Because we're talking about 1 mole of something here. So maybe I'll add that just because that's the way the units are usually reported. Okay? So 213 joules per Kelvin times mole. Is that the right sign? It's always good just to check at the end and make sure we have our sign correct. Okay? We already said delta S for this process should be positive, so that's good. Okay? All right, so that's how you would figure that out. Now again, are you going to see that on an AP exam or even my test? Probably not as a calculation-based question. I just want you to have some idea of where the delta S comes from. Yeah, that's true. You could just look at the units and then you'd have some idea that it's related to energy. All right, next one. Calculate the delta G for the following reaction and indicate whether it's spontaneous under standard conditions. Alright, so I'll let you give a shot at this one and then we'll talk about it in a minute. Okay, so let's go ahead and talk about this one. You're going to solve this problem very similar to the way you solve a delta H of formation problem, okay? And the thing you have to remember here also is that the delta G of formation for any element in its natural state is also 0, just like the delta H of formation. So you don't need the O2 data for this one, okay? Alright, so we're just going to do products minus reactants here, okay? So the product is the SO3, negative 370.4. And that's kilojoules per mole, okay? And then we have to multiply that by the number of moles that there are in the reaction itself, which is 2, okay? And then we need to subtract the delta G of formation of the reactants, okay? Now the reactant that we need to worry about is the SO2, okay? The SO2 is negative 300.4. And again, this is per mole, and I believe there are 2 moles of the reactant as well, right? Okay. So once you calculate all of that, your delta G should be, I'm getting the number negative 1341.6. Is that what you guys are getting? No? Negative 140? Okay, I may have messed up my sign on that one. Let me double check. Let me try this again. Negative 300.4 times 2. Oops. 740.8. 600.8. There we go. Yeah, negative 140. I'm sorry. Probably should have been able to. Yeah, don't tell me what I should be able to do in my head. Okay. Because we all know that I can't do much in my head. So, negative 140 kilojoules right here. That's what you should be getting for this one, if you did better than me. Yeah, it's just kilojoules, but that's not the right number of sig figs. Because if we take these two and subtract them from one another, each of these, their last significant figure is the decimal place right there. So really the correct answer here is negative 140.0 kilojoules. The question on the previous slide was whether calculate the delta G for the reaction and indicate whether the reaction is spontaneous. Okay, so under standard conditions, which is where we are right now, so I guess we could call this delta G 0 because that stands for at 25 degrees and 1 atmosphere of pressure. Our delta G is negative. What is that telling us? This is a spontaneous reaction at this temperature. Okay, next. Question 9. Explain qualitatively how delta G changes for each of the following reactions as the partial pressure of O2 is increased. Interesting. Okay, I'll give you guys a minute to think about this one. Okay, let's go ahead and talk about this one. Now, there are a couple different ways to think about this one, okay? I'm going to show you the way using the formula first. Okay, now this formula is not on your AP exam sheet, your formula sheet, so this might be a little less useful, but I'm going to show it to you, okay? There was a formula that went with this, and the formula is delta G is equal to delta G 0. I believe it's plus RT ln Q. You guys remember that? So that's how you can relate delta G to delta G 0, okay? And so basically, delta G 0 is when we're at standard conditions, okay? As soon as we start increasing the partial pressure of the O2, we're not going to be at equilibrium anymore, right? So we're sort of disturbing the equilibrium. Now maybe I should have written these as forward and backwards arrows to give you a little bit more of a hint here, okay? But you can sort of think about this in terms of Le Chatelier, okay? Well, okay, before I think about it in terms of Le Chatelier, let's think about this. This Q right here, Q for this particular first reaction. Let me do this on the next slide, okay? So Q for this first one here is going to be CO2 squared over CO squared times O2, right? So the pressure of the CO2 squared over the pressure of the CO squared times the pressure of the O2. That's, better fix that. Okay, so that's your Q, and you can kind of think about this, again, in terms of Le Chatelier or in terms of what it's going to do to Q. If I start increasing the pressure of the O2, what is that going to do to my Q? Make it smaller, okay? So if I make it smaller, what does that do to the natural log here? When I take the natural log of a smaller number, it gets small enough, eventually this is going to become negative, right? Okay, so then that's going to make my delta G actually decrease. Okay, so that's one way of thinking about it. Now another way is just using Le Chatelier conceptually. Okay, so if I add O2 into this reaction, which way does that push the equilibrium? Pushes it to the right. Okay, and another way of saying that is it's going to be more spontaneous in the forward direction, which means that my G would decrease in that particular instance. Does that make sense? You can kind of think about it either way, okay? So for A here, delta G would decrease or become more negative, however you want to think about that, okay? It would move closer to spontaneity if it's not already there. All right, for B, now that we sort of have that framework in mind, we should be able to answer these fairly quickly. What's going to happen on B? Okay, now we're adding a product, right, which shifts the equilibrium back this way, okay? Which, again, if we're thinking in terms of K, that's going to make the K smaller, okay? And if the K is smaller, then the way that relates to the delta G is typically the delta G becomes more positive at that point, okay? All right, so for B, the delta G would increase. And then for the last one here, for letter C, again, the oxygen is on the right side, on the product side, so that's going to do the same thing as the second one. Delta G would increase. Okay? So I want you to understand how the equilibrium, how changing something, changing a pressure, can actually affect your delta G. Okay, you got to think about it in terms of Le Chatelier. All right, question number 10. Calculate the equilibrium constant at 298 K for the following reaction, and the only thing I've given you is a delta G of formation and a temperature. Okay. So let's talk about this one real quick. We're calculating K, and they're giving us a delta G, so that's probably going to have something to do with the delta G equals negative RT ln K equation. And again, this one's on your equation sheet. So delta G equals negative RT ln K. All right, now the delta G for this reaction we can find fairly easily because this is giving us the delta G of formation for HI. The only thing we need to change here is what? This is giving us per mole, right? How many moles of HI are we forming here? 2, so we need to multiply it by 2, okay? So 2.60 instead. So we're going to end up with 2.60. Okay, here's the other place you have to be really careful on this particular calculation. The R here is 8.314 joules per mole times Kelvin. Okay, it's on your equation sheet. All right, so we have to keep the units the same. The easiest thing to do here is to change this to 2,600 joules instead of 2.60 kilojoules. Okay, that's going to be equal to negative 8.314 joules per mole times Kelvin times the t, which is 298k, times the natural log of k, which that's what we're eventually going to be solving for here, okay? Once you work all this out, the natural log of k, what I was getting was that that's going to equal negative 1.049. Hopefully that's right. Has anybody worked that one out all the way? That's what you got? Okay. So then to solve for k, we need to do what? We need to e it, right? So k is equal to e to the negative 1.049 power, which is equal to 0.350. So the correct number is sig figs, I believe it should be 3. Okay? So there's your k for that reaction. Okay? And that's how you would solve that one. I don't think we're going to have time for the last one, so I will just make a final video going over the last one that I will also post online. Okay? Make sure that you're studying for this test. I want you to do well.